Continuing with work, energy, and power, we looked in our last video at the idea of work being done when a force moves something in the direction of that force. One possibility would be that we could have a force that varies in some way according to distance or displacement, and we want to be able to, from a graph of force versus displacement, figure out the amount of work done, and that would be given effectively by the area under the graph. If we think about the units, when we work out the area, we have effectively multiplied force times displacement. So we could just write in our notes that work done equals area under a force displacement graph. Right, so that's work dealt with. Let's move back now to our ideas of energy and just revisit kinetic energy and define what we mean by kinetic energy: the energy possessed by a body due to its motion. And let's derive the formula for kinetic energy. So if we consider a mass little m, so here is our mass little m, initially at rest, to which a force F is applied to give it acceleration little a, so it moves through a displacement S. Alright, so initial position here, final position there. It starts from rest. The work done by the force would be given by F times S. But from our stuff to do with dynamics and Newton's laws of motion, etc., we could therefore say that the force is mass times acceleration times S. So we've got that statement there. Now the work done is going to be equal to, I'll put it this way, the change in kinetic energy might be a better way of expressing it. Delta EK is going to be equal, therefore, to MAS. And since the body starts at rest, its initial kinetic energy would be 0. So therefore, the final EK would be given by MAS. Right, now what we want to do is get rid of the AS part from here. And so we're going to hark back to our equations of motion. V squared equals U squared plus 2AS. Just a bit of trickery. In a sense, there's our AS. We want to make that the subject in the equation and then substitute that over here in place of the AS. Alright, so V squared minus U squared equals 2AS. AS equals V squared minus U squared divided by 2. But again, since the initial velocity of the mass is 0, then over here U is 0, so we can get rid of U, and we end up with AS being equal to V squared divided by 2. Let's just shift this thing out of the way, just so we can write down here. Therefore, EK equals M times V squared over 2, or 1/2 M V squared. There is our formula for kinetic energy derived. You need to know that derivation. Alright, to define what we mean by potential energy, first of all, in general, potential energy is energy that is stored. Now, it can be stored in lots of different ways. One form in which it can be stored is as elastic potential energy. A little bit later in the course, you'll come across this also called strain energy. Alright, and we would say that elastic potential energy is the energy possessed by a body due, or now let's put it this way, let's say energy stored due to the deformation, the change of shape, due to the deformation of a body. Chemical potential energy, those who study chemistry would realize that it's all about bonding between either covalent type bonding or ionic bonding, all to do with the giving and taking or the sharing of electrons. So chemical potential energy is really energy that is stored, whoops, due to the bonding of atoms and molecules, let's say. And then finally, gravitational potential energy. That's energy that's stored due to the position of a mass when it's placed in a gravitational field. If we change its position in the field, we change its potential energy. So energy stored due to the position of a mass in a gravitational field. And again, we have our formula, which you are, I think, familiar with, mgh. Well, you need to be able to derive that formula. So we've got here a mass little m, and since it's got mass m, is going to have weight mg. Now, if I want to hold this mass steady, I would have to apply a force F, this force here, equal to the weight. And if I want to move that mass at a constant velocity upwards in that gravitational field, again, if it's constant velocity, I would have to be applying a force equal to its weight. All right, and so the work done in raising that mass through vertical height h, first of all, in general terms, F times S. In these particular terms, mg, that's the force, mg, times the distance or displacement in the direction of the force, h. So the work done is mgh, but that's going to be equal to the change in potential energy. So therefore, delta EP equals mgh. And if we just have a look at our learning outcomes and just double check how it is expressed there, it does just say mgh. So there is our formula. Very easy to derive that formula for. Really, it's for the change in potential energy between one point and another in a gravitational field. All right, let's have a look at an example. We've got a roller coaster rolling down a track as shown. Starts at 15 meters above the ground, travels along some sort of a curved path, and it's got an initial velocity of 5 meters per second. So at the top, we've got both kinetic energy and gravitational potential. At the bottom, we will only have kinetic energy. All right, so conservation of energy is what we're going to use here to figure out how fast the roller coaster is going at the bottom. So first of all, EP at top equals mgh. I normally like to line the equal signs up, but I'll have to just cheat a little bit, come over here just to squeeze things in. Okay, so it's going to be 200 times 9.81 times 15. And work that one out. Just plug the numbers into the old calculator. 200 times 9.81 times 15 equals 29430. Now EK at top equals a half mv squared, a half of 200 times 5.0 squared, 100 times 25, 2500 or 2500 joules. So we've got those two lots of energy, most of it's potential, a little bit of kinetic, total energy at top, going to be those two numbers added together, 29430 plus 2500, 31930. So if that's the total energy at the top, then that's going to be the total energy also at the bottom. I think we're going to just need to create another page here just to be able to finish the working off. Just do that. Okay, that'll do. Remind ourselves of what was on the previous page. I think it was, oh, where have we gone? Sorry, hit the wrong button. What was our figure again? It was sorry, 31930. We'll get there. 31930. All right, that's the key number. 31930 joules. All right, so we can say EK at bottom equals that number over there. So a half mv squared must equal 31930. A half of 200 v squared equals that. So v squared equals 31930 divided by 100 equals 319.3. Don't forget at the end of the problem to take the square root, because if you forget that, well, you ain't there. Right, square root of 319.3. 17.87, make that 17.9 meters per second. Now it's an interesting little question to ask ourselves that this problem had a mass of 200 kg. What would happen if we changed the mass of the roller coaster? How would that affect things? I want you just to think about that, and it's something that we can discuss together.